Hello, hi, welcome to science class. We will study Doppler effect. In science, the Doppler effect is related to expanding universe and eventually Big Bang theory. Let's go for Doppler effect in this video lecture. Doppler effect is all about the light. Before we go for Doppler effect, let's study about the light a little bit. The light has a wavelength. The light is a kind of wave and do some oscillation and moving. One oscillation is one wavelength of which length are between crest and crest. Between the crest and crest we call wavelength. So some lights have a short wavelength, some lights have long wavelength. Amplitude is the height of the crest. High amplitude means higher energy. The frequency is number of waves that pass by each second. Look, these are two different lights. One is the red color with longer wavelength and the other one is blue color with shorter wavelength. Let's count the frequency for this red light. Frequency is the number of waves that pass per each second. So 1, 2, 3, 4, 5. Okay, what about the blue light? Okay, let's count. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so see the blue one with a short wavelength has more numbers of frequency. We call it high frequency. For red one with long wavelength has less numbers of frequency per each second. Okay, we call low frequency. So what are the lights? You probably know the visible light, which means we can see. There are 7 colors variation: red, orange, yellow, green, blue, indigo, violet. Which one is shorter wavelength? Violet. Which one is longer wavelength? Here, red one. You know, there are so many things we cannot see in our universe. Human eyes are so limited. There are much shorter wavelengths of light: ultraviolet rays, X-ray, gamma ray. Look at the name of the light next to the violet. Ultraviolet, which is UV rays. We get lots of UV rays from the sun. X-ray, you get the X-ray at the hospital. Even you do not see the X-ray, there is something penetrating light to your skin and bones. Gamma ray, if there is an atomic bomb, lots of gamma rays coming from the atomic bomb explosion. It's so strong we cannot survive. Now let's look at the longer wavelengths: infrared ray, microwaves, and radio waves. Infrared ray is kind of thermal energy. Human body gives infrared energies. So there is infrared goggles for night vision. Microwaves, we use microwaves to warm up the food. Radio waves are radio, FM, AM, TV sounds. So here we see, you will see 2 color directions for blue color and red color. Shorter wavelength light gets stronger, longer wavelength gets weaker. So blue color side, shorter wavelength, strong, higher energy, high temperature. We will study soon. It is blue shifted, moving toward to you. Red color side, long wavelength, weak, low energy, low temperature, and also we will study soon about red shifted, moving away from you. Okay, What about the speed of light? Nowadays, we can measure the speed of light. When you turn on the light toward the mirror, the light is reflected, and then the machine can detect the moment of the light returns. If it takes 2 seconds and the distance is 186 miles, 300,000 kilometers, then we can calculate the speed of light using distance divided by time. So speed of light is very, very fast, but it is not unmeasurable. Speed of light is 300,000, speed of light is 300,000 kilometers per second. Now let's get into the Doppler effect. It is related with red and blue light. Okay, Doppler effect, red and blue. Okay, here is the question. What about the speed of this red and blue light? They are same. Red light, blue light, their speed of light are same. 300,000 kilometers per second. So red light, long wavelength, low energy, low temperature, low frequency. Blue light, shorter wavelength, higher energy, high temperature, high frequency. The speed of light for all wavelengths are same. The speed of light is 300,000 kilometers. Doppler effect is related with those light waves. The thing is that waves change. Waves compress or relax with relative motion. Compressed means shorter wavelength equals higher frequency. Relaxed means longer wavelength equals lower frequency. A stopped train sounds different than a moving train. So as the train approaches, a person hears a higher pitch. As the train passes, the pitch drops higher to lower. As the train recedes, a person hears a lower pitch. Here, there is a car with a siren. Nobody moves. And there is a girl with a Korean costume. As she stands here, and the siren coming out, the car, stop the car, and here is the original wavelength. Car comes toward to you now. So during it gets closer, the wavelength of siren gets shorter. Shorter wavelength is blue color. Blue color side, higher frequency, high energy, high pitch. So direction to blue color side, wavelength gets shorter toward to the direction of the blue color. We call this blue shifted. So blue shifted wavelength. Okay, now the car moves away from you. So now the ambulance with siren moves away from you. When it goes away, wavelength of the siren gets longer. It becomes longer wavelength. So we know red one has a long wavelength. The wavelength moves toward to the red color side, which has low frequency, low energy, low pitch. Direction to the red color side, wavelength gets longer to the direction of the red color. We call this red shifted wavelength. Okay, so this is Doppler effect. Nobody moves, nothing changed. it has the original wavelength. Okay. Car comes to you. Wavelength gets shorter. Direction to blue color side. Blue shifted. This doesn't mean blue color itself. It means blue color side changing, shifted. Car moves away from you. Wavelength gets longer. Direction to the red color side. We call it red shifted. Again, the car comes to you. Wavelength gets shorter than the original wavelength. Look at the spectrum here. Red color with longer wavelength and blue color side with a shorter wavelength. Here is some absorption spectrum, and it shows the changes toward to the shorter wavelength side, which is blue color side. See, this doesn't mean blue color itself. It means blue color direction shifted to blue color side. Okay, so the interpretation of the Doppler effect, scientists has a spectroscope to observe the spectrum. Scientists observe the wavelength gets shorter, blue shifted, then the object comes toward to you, which means the distance between the object and you or me or scientists gets closer. If you have blue shifted Doppler effect with something, then you and something gets closer. What about this? Car moves away from you, wavelength gets longer, direction to the red color side, red shifted. If you see the spectrum, the absorption line moves toward to the red color side with longer wavelengths. What about the interpretation? The interpretation of the Doppler effect, if you observed wavelength gets longer, red shifted, from the spectrum, object goes away from you, which means the distance between the object and me gets further apart. What can the light from distant stars and galaxies tell us? When an object such as a star or galaxy is moving toward us, the wavelengths of the light it emits are shifted toward to the blue end of the spectrum. Frequency is shifted higher. This is called blue shift. If the object is moving away, its light is shifted toward the red end of the spectrum. Frequency is shifted lower. This is called redshift. This phenomenon is shifting of wavelengths due to the relative motion of the object is called the Doppler effect. So you have experienced Doppler effect every time you listen to the car drive by. As the car is approaching, the pitch is shifted higher, and as it passes and it moves away, the pitch frequency is lower. Did you hear? So here is the okay. So here is our sun's spectrum showing the range of the visible light. The visible light wavelength ranges from 400 and 700 nanometers. So more like 400 nanometer is blue color with a higher frequency, and 700 is red color side, red color part, lower frequency. You see several black lines here in the spectrum. We call observed spectrum with a certain element composition. Anyway, this observed spectrum is from our sun. Now, we look at the distant galaxy spectrum. So moving light waves reveals the Doppler effect. Light moving towards an observer compresses. Light moving away from an observer expands. If you look at carefully, you will find out the lines are similar. Here, simply move toward to the red direction, redshifted. See? Which is redshifted. Okay? What is your interpretation based on the Doppler effect? The distant galaxy is moving away from the sun. With the wavelength changes, the speed of the movements can be estimated. If you know the wavelength of light you are observing as well as the wavelength of light the object would be emitting, if it were at rest, you can find the speed of the object using the Doppler effect. Okay? So literally based on Doppler effect, we can calculate the speed of the object moving. Isn't this awesome? Here one of the sun's black observed line is 656.3 nanometer, original wavelength, or we can see the wavelength at rest. We can say the wavelength at rest. Then the observed one from the distant galaxy with redshifted is 659.0 nanometer. So 659. The speed of the distant galaxy can be estimated with this formula. Don't worry about the formula, no need to memorize. We estimate the difference with the speed of light, then we get the speed of the galaxy, 1.2 million meters per second. So our interpretation is that the distant galaxy is moving away from us, from Earth, from the solar system, from Milky Way. In a speed of 1.2 million per second, we are getting further and further away. Thank you very much.